Hi, so I'm continuing functions in this lecture as part 2, and we'll be discussing domain, equality and composition of functions in this lecture. So first of all, domain of a function. Basically, the calculus we are studying is purely based upon real numbers. A real number is the basic set on which we start our functions definitions. So in general, what domain is? Domain is a set of real numbers excluding those points on which function is not defined, right? So we need to find those exceptions where the function is getting infinite values or function value is not defined in any case. So that points must be excluded from the set of real numbers and rest will be the domain. So if there is a point x on which function is undefined, that point must not be the part of domain. Alright, so I'm taking different types of functions to discuss the domain of a function, and this will tell you the applicability of how to find domain. So first of all is a normal, first function is a normal polynomial 2x plus 3, second one is square root function, third one is piecewise defined function, fourth one is a function that contains one of the trigonometric ratio, and the fifth one is a rational function in case of polynomial, and the sixth one is a function with prescribed restriction, means restriction already is given there. So we are discussing one by one. In first question, fx is equals to 2x plus 3, there is no point where the function is not defined. You can easily check the function is not going to infinity. In any case, in any real number substitution for x you are doing, there won't be anything absurd that will be coming as an output. So there is no point on which function is undefined. Hence the domain in this case would be all real numbers. And this is a short way of writing DOM, F and R is for real numbers. Second one is a square root function, and we clearly know square root is not defined for negative values in case of real numbers. So the condition is x square plus 2x must be greater than equal to 0 if you want function to be defined. So to solve this, we solve it by factorizing. The factors are x and x plus 2, and we want the positive value. The x is equal to 0 and x is equals to minus 2 are the factor. Plot them on the number line. Minus 2 will lie at the left. And we'll start with the partition. We'll start with the sign plus and alternate sign plus minus plus. And you want the positive sign. The positive sign is visible for the region minus 2, below minus 2 and afterward 0. Right, so domain will be minus infinity to minus 2 union 0 to infinity, where you can observe the positive sign because you want x square plus 2x to be positive, and still equality is there. So minus 2 and 0 will be included, and hence they are having close bracket in the answer. So the next is piecewise defined function. In piecewise, we need to check there is no point left from the real number which we cannot put in the function, plus for any value we substitute we are not getting infinity. So these are the two things we need to check. One, it is defined for every real numbers, means you can check function is defined for x less than equal to 1, means 1 is also covered, and x greater than 1, so all the real numbers have been covered. Plus in the both definition of function is not going to be infinity. So domain is real number. In fourth case, 4 upon 5 minus cos x, function is defined whenever the denominator is non-zero. So 5 minus 4 cos x should not be 0 if we want function to be defined. In this case, we will be getting cos x cannot take value 5. So this is the only restriction we are getting. But surprisingly, cos x never crossed the value 1. Maximum positive value of cos x is 1. right? So cos x will never take the value 5. So there is no point which need to be excluded from the domain. Its domain is real number, no restriction. Next is we have a rational function with polynomials. So you can easily observe students generally do this as cancelling x plus 3 common part and getting the answer 2x minus 1, but they need to understand this. You can only cancel those values which are non-zero. So you need to mention over here that x plus 3 cannot be 0 if you want to cancel this. So function will be 2x minus 1 when x cannot be equal to minus 3, and then 2x minus 1 is feasible for all, means is defined for all real numbers. So domain will be all real numbers except minus 3. Last one is fx is equals to 2x minus 1 and x cannot be minus 3. This restriction is predefined given in the definition of the function. So we need to exclude that preferably. Otherwise there is no restriction. 2x minus 1 is defined for all. So domain will be all real number except minus 3, sorry. So the next is equality of functions. Two functions are equal. F and g are the two functions. They will be called equal if both these criteria is fulfilled. Generally first of the criteria students forget. The foremost criteria is both function should have the same domain. This is the foremost criteria. After that, second criteria says they should attain same value for each value of the domain, right? But students remember only this part. First of all, domain should be same. Second of all, they should have equal values for each and every point of the domain. So for question I'm discussing as an example which will clear this fact why domain is necessary. So there are three functions. Fx is equals to 2x minus 1, gx is equals to 2x minus 1 with restriction, x cannot be minus 3, and hx is a 2x minus 1 x plus 3 upon x plus 3, which we have discussed just before this. So does the function hx equal to fx or gx or both? So in solution you will see, if you write hx is equals to 2x minus 1 x plus 3 upon x plus 3, I have discussed already, you cannot cancel the term which is 0. You can only cancel if it is non-zero. So you need to mention here x cannot be minus 3 is the domain of hx. Domain of hx is all real number with exception of minus 3. So hx cannot be fx because fx is defined for all real number. There is no restriction of minus 3 in fx. But in gx, yes, there is a restriction of minus 3. So hx and gx are the function which have same domain, and hx and gx are equal for every point of the domain. So that is why hx and gx are equal function, but fx is not equal to any of them. So this you need to make it clear. Domain is the first preference for equality. Domain should be equal. After that, values at every point should be equal. So this is equality of functions. I hope it is clear. So next thing we are discussing is composition of functions. So this is a situation when a function of one variable in turn is a function of another variable. Then we use composition of function. A function of one variable can be written as a function of another or second variable. Then we use, or rather I should say we need composition of function. Now to understand this, first understand this practical applicability of composition. Suppose you need to deliver some packages via courier, and it depends, obviously the cost of shipping depends upon the weight of the package, and weight in turns depends upon the number of objects, because the specific objects contain some weight. So suppose x is a number of object and fx is the function which tells you about the weight as per the number of objects already in the package, and gx is defined as the cost of shipping because cost of shipping depends upon weight. So virtually you can see x will give you fx, means number of objects will let you know about the weight of the package, and weight in turn will let you know about the cost of the package. So in turn gx is connected to fx, which is the number of object. So this is what composition situation is. X is the domain for fx, then fx is the domain of gx. So here on gx I should write g of fx to make it better, and g of f, which is a composition function, can be written as g of fx. So for the basic definition, yeah, rather I should say the mathematical definition of composition function is f of gx is equal to f of gx, where x will give you the value gx via function g, and g of x then will work as the domain for f, and this will give you the range f of gx, and this is defined for every x in the domain of g, which is further g will be the domain of f. So to find composite functions, composition of functions, when two functions or individual functions are given to you, like f of t is root t, g of t is t square, and we are finding the composite functions. When you are writing f of g, first g of t will be applied, f of, I'm sorry I have written it incorrectly, f of t square, first of all g of t will be applied, it will be t square, and then on f it will be square root of t square will be t. Similarly you can find g of f. G of f is also coming out to be t. Both are equal, but in general it's not like that. Here in this case f of g is equal to g of f because functions are that way. They are kind of reciprocal functions. One is square and other is square root. In general they are not same. F of g is not equal to g of f in general. So to understand this, we have another example where they are not same. Suppose function fx is 1 upon x, g of x is tan of x, and f of g of x will be, first of all you will apply gx, that will be tan x, f of tan x will be 1 upon tan x. And similarly when you will calculate g of, where you will first write f of x and then apply g of x, it will be tan of 1 upon x. Both are different values. 1 upon tan x and tan of 1 upon x. Both are different functions. So they are not equal. So another concept is where composite function is given to us and we need to find the inner and outer functions. Means we need to bifurcate into two different functions. Now composite functions are given to you. F of x can be written as g of u of x, where composite functions are given. One is 2x square minus 1 whole to the power 4. Second is square root of 5x minus 1. Third one is sine of root x. Fourth one is sine of x plus 1 upon 2 minus x. So first of all, the given function is a composite function. We are writing this f of x is equals to g of u of x. And we need to find g and u. As per this composition, we need to find two different functions, g and u. U is the inner function, g is the outer function, right? So inner function will be ux, outer function will be g of u. So in fx you will see what is inner function. First of all you need 2x square minus 1 and after that you need power 4. So afterward function is u to the power 4. In second you see fx is equals to square root of 5x minus 1. Inner function is 5x minus 1. After that you need square root. So g of u will be root of u. in sine of root x, first function is root x, and afterward function is you will apply sine, so it will be sine of u. Same is the case in D part. Sine of x plus 1 upon 2 minus x. Inner and outer function can be specified this way. Thank you.